Okay, so what were we looking at yesterday? So we were starting to look at the ideas of streams yesterday. So we had looked at motivations. We started to look at how you might program with streams in OCaml, right? OCaml allows you to do infinite data structures, um, but what we were grappling with is how do you actually manipulate these infinite data structures in any useful way? Like we were trying to write this map function and it was failing. So in order to refresh our memory, let's just look at what we had last seen and then we'll continue. So we observed that we could define a stream data type as a new type, an alpha stream, which doesn't have a null because streams are infinite. And it only has a cons constructor where you have an element, right, which is the alpha, and then the rest of the stream. Okay, so in order to construct a stream, you have to use this constructor cons, for which you always have to provide another stream as a value. And the only way to construct this, if you sort of think about it, right, because you don't have nil, the only way to construct a value of this type is to have a recursive value. Okay, so we had this. You can construct a stream of zeros and ones, right, using this by using the letrec on values. Just to recall, OCaml allows letrec on values as well, in addition to functions. When you have a recursive function, you can call it recursively. When you have a recursive value, you can essentially tie the loop. And what is happening here is we are constructing a recursive value called 0 and 1, which is a you can think of this as a linked list node, right? A linked list node with 0, which points to a node which has 1, whose next pointer points to 0 again, right? It is 0 once again. So it's a small linked list with only 2 nodes, but has a cycle in it. So 0, 1 and points back to 0, right? So we construct that. We see that this is a stream which has a 0 and a 1 and has a cycle here. So the OCaml pretty printer just doesn't print that it is 0 once, but we know that this is pointing back to 0 once here. So if we write a recursive function toString, which takes this stream of zeros and ones, and we want to convert this to a string, naively you can do string of int of the head to convert the head element to a string, and then recursively apply toString function on the tail, right? Because the list is cyclic, this function will never terminate. So here is what we see, right? We saw this yesterday. So when you apply toString on 0 once, this infinite stream, we get a stack overflow because the function doesn't terminate. So the observation was that we have to somehow pause the execution, right? And what do we mean by pause the execution? We need a way to pause the execution at the tail position, right? So we need to do something at the head, but at the tail, it might be the case that we are back to the head. So rather than recursively applying the function that we want to apply on the rest of the list, we want to say, okay, I've done the operation that is necessary for the head, but for the tail, I'm just going to not do it unless it is certainly required, right? So that is the idea of pausing the execution. And in order to pause an execution, we have seen ideas previously, right? We had this idea of a thunk. A thunk is just a function that goes from unit to alpha. The idea is that whatever expression you have in this thunk is not evaluated until you call that function. Right? So you can take arbitrary expressions and wrap it in a thunk so that it doesn't evaluate until you actually call the function. So here is a simple example just to remind you of what a thunk does. So I am declaring a variable v, right, which is the result of fail with error. I don't know whether I introduced fail with earlier in OCaml. This just raises an exception called error, right, with this message. So when I evaluate this particular definition, I immediately get an exception, which just says exception name is failure, and the string is error, and it immediately throws me that, right? So you can sort of pause this error being exception being thrown immediately by wrapping this in a thunk, right? All I've done is I've sort of created an anonymous function here, where now what I have is a function, which when I run, I get a thunk, which goes from unit to alpha. Alpha because any exceptions have an alpha type. When you raise an exception, that expression has an alpha type. So it doesn't raise an error when you define it, but when you actually call it, you get an error. You get the exception. This shouldn't be surprising, right? But what we are going to do is to use this idea in the definition of a stream that is usable. Okay, so the key point that we are going to use is the notion of doing a thunk, which will pause the execution. So how do we use this? So we are going to look at the same stream definition again, but now what we are going to do is to use thunk for pausing the tail of the execution. So I'm redefining the stream type as a new type. The type is alpha stream, right? It has a single constructor cons, which takes which has two things, right? It has the alpha value, and the tail is now a thunk, right? Tail is actually a unit to alpha stream thunk. So that's what will give us the ability to pause the execution, right? Rather than having an alpha stream directly, we have a unit to alpha stream, right? So how does this help us? So first, let's construct a value, a recursive, an infinite stream of zeros and ones. So as usual, let rec 0 ones, right? First we have 0. Then according to the type, I should have a thunk here. So I have a anonymous function which takes a unit, and the tail is cons 1, right? That's the 1, and the tail of that is going to be another thunk, which points to zeros and ones. So all we've done is we've sort of introduced thunks at two places, right? Rather than directly pointing to the next node, we have a function, anonymous function that is sitting there. How does this help us? Let's sort of slowly build it up. So we want to eventually go to this map function, right, which maps over the entire list and then converts all of map over the entire stream and then convert each of the integers to a string. So let's define helper function first. So I want a helper function for getting the head of the stream. So I define this function head, which just returns the head of the stream, which is the value in the cons. We only have one constructor, right? So we can match it at the argument position itself. So we are defining a function that pattern matches cons, extract the x, and then simply returns the x. So the type of this function will be give me a stream and I will give you a head, right? And what about the tail function? So because tail is a thunk, in order to get the stream, you have to call this function. You have to apply this thunk in order to get the stream that is embedded within it. So tail is defined such that extract this thunk, excess is actually a thunk here, right? Because of this type. And now call this function. If you call this function, what you will get is a alpha stream out. So tail is a stream to stream. So given a stream, it returns you the tail of that stream. And in particular, what it does is it actually calls the thunk, right? So the point here is this, right? So tail is the one which is actually going to evaluate the function. So if you're just looking at head, you're not going to evaluate that function. But when you say, I actually want the value of the tail, you go and evaluate. So that is what is giving us this, going to give us the ability to not keep doing all of the operations when you map at the position of mapping. Okay, let's see how this works with more examples. So now I want to define this function called take, right? Take ns, takes an integer n, right, and a stream s, and returns a list with the first n elements of the stream, right? So I have an infinite stream. All I want to do is to get the first n elements, right? So how do you do that? So you define it as a recursive function, right? Takes an n and an s. If n is 0, then you just return an empty list. So you want 0 elements, so you just get an empty list back. If n is non-zero, construct a list such that the first element is the head of the stream, right? Head is what we had defined in the previous slide. And you recursively call take on n minus 1 and the tail of the stream, right? And at this position, when you actually want the tail, the stream trunk is evaluated, right? So you recursively call this until you reach the end. And this is not tail recursive, but that's not, that's not a problem here. So, this should be fairly standard, right? This is the exact function that you will write for taking, say, n elements from a list as well. We've sort of hidden all of these smarts within this tail function. Okay, so nothing surprising here. So that's the tail, the take function. It takes an integer, it takes a stream, and then returns n elements from the stream as a list. So we had defined the 0 ones stream earlier, right? Which is an infinite stream of zeros and ones. Let me just take the first 10 elements from it. So I get 0, 1, 0, 1, 0, 1 repeated 5 times. Okay. So that's the, that is this function in action. And we can also define a drop function, which drops the first 10 elements from a stream, right? So give me a stream, give me n, I will return you a new stream such that the first n elements of the given stream is dropped. So how do you define that? It's a recursive function, right? If n is 0, then just return the original stream. You're not dropping anything. If n is greater than 0, then you just recursively call drop with n minus 1 on the tail of the stream. So by simply recursing on the tail, you're dropping elements, right? You keep doing it until you reach 0. So that's the definition. So what do you get? Drop takes an integer, it takes a stream, it drops n elements from the stream to get you a new stream. Okay. Okay. So that's done. So just to make sure that it works, right? We had the 0 1 stream that we defined earlier, which is 0 1 0 1 0 1 0 1 and so on. If you drop one element from it, so this element 0 is dropped, what you get is an infinite stream that goes 1 0 1 0 1 0 1 0 1 0 and so on, right? So which is what you'll see here. So if I run it, it prints 1 comma, that you can sort of take 10 from drop 1 0 once. So 1 0 1 0 1 0. So you can do as many elements as you want. This is an infinite stream, so it doesn't matter. So you can keep yeah. So this is an infinite stream. Okay, so that's take and drop. So now let's actually look at the function that we wanted to define. Right? What we want to do, we wanted to define a map function, right, which maps a given higher order function over the stream. So here is the definition of the map function, right? Map is a recursive function that takes a higher order function f and a stream s, and what it's going to do is to map this higher order function on every element of the stream. So this is where we failed earlier. If you remember, we tried to do toString on this infinite stream of zeros and ones, and we failed. So what is different here? The difference is this thunk, right? First, the obvious ones. So this is a stream. So we are going to return a new stream. So it's going to be a const value, right? Where the head element is such that it's the original head where f is applied to it. So f applied to the original head is the new head. And for the tail, we are actually creating a thunk which maps f on the tail of the list, tail of the string. So that's the key bit that makes it work. By actually creating this as a thunk, right? You're not doing map when you call this function once, right? So when you call this function map, you are only doing f on the head, and all you're doing is you're creating a thunk, which when applied, when you want to get the tail or something, that is exactly when you apply this rest of the map on the tail of the list. And it's a recursive definition, right? So If you wanted, say, for the first 10 elements, you will only do map on those first 10 elements, right? You will only apply this f on those first 10 elements. You won't apply it on the rest of the stream. That's the key bit. So every time you actually do a map, we sort of create this thunk, right? So what's the type of this map? It takes a higher order function that goes from alpha to beta, right? Give me an alpha stream, I will return your beta stream. So here's the thing that we failed earlier, right? So I have a stream of zeros and ones. I am now mapping string of int function, which takes an integer and returns you a string over each of these elements in the stream. Of course, the stream is infinite. All you're getting is the infinite stream back, right? So if you apply this, you get a string stream. 0 ones is an integer stream. Now you get a string stream where we just print the first element. We are not printing the rest of the element because that's a function value, right? You can see that it works by, say, taking 10 elements from 0 ones string stream. So when you take the first 10 elements, you see that you see what you expect, right? So this is 0 1 0 1 0 1. Each one is a string now. Yeah, okay. So this is how we make it work. Do you have any questions so far on this? We'll look at more ideas in the next step. I'll wait a minute to sort of clear out any questions before we look at more advanced uses of streams. Yeah. Sir, in the case of repeating streams, why can't we just map one cycle? Good question, right? So you're asking a really good question. So the point is, once you construct this value, right? So what you're asking is, if you know it is actually a cyclic list, why don't we just map it once? So the thing that you need to do is you need to identify that there is a cycle, right? So of course this can be done for our use cases here. So here we construct actually a cyclic list, right? You have to use some methods which are sort of more low level. First thing, right? Taking a step back, you have to use some notion of physical equality in order to detect the cycle, right? So you have to sort of say, use the usual cycle detection algorithm that you have for linked list to detect the cycle, and then you can do this idea. But that will work, Raghu. But what we are building here is we are building operators that can operate on real streams, right? Here we are sort of simulating streams with cyclic lists, but think about um, a socket or something, right, where packets keep coming in. So there is no data structure there. It's just like a tap. You cannot walk over the data structure anymore. But these sort of functions will still work. So that's the idea there. Yes, you are right. You can um, use your standard ways of doing cycle detection to do one mapping over the cycle. I would suggest try it, right? So can you get the same programming interface with that? Essentially, what you want is you want a map which knows when to stop. See whether you can do it. It's an interesting question, certainly. Yeah. Any other question? Okay, so if not, I will continue. What we're doing? Okay, so we did this. So the next useful function that we are going to see is filter. So what does filter do? Filter is a function that takes a predicate, okay, that and a stream. And the idea is that this predicate is a function that when applied to an element in the stream, it returns a Boolean, right? So what we are going to do is to return a new stream such that every element that satisfies the predicate is removed. Okay, so take the stream, take this predicate, apply this on the stream. If there are any element that satisfies the predicate, remove that and return a new stream which doesn't have any of those elements. Okay, so that's what filter is going to do. So how do we define filter? So it's a recursive function. Filter takes a predicate and a stream. And if the predicate applied on the head is true, then the head value should not be in the resultant stream, right? So we recursively call filter on the tail of the stream, right? If the predicate does not hold on the head element, then the head element is going to be present in the resultant stream. So we create a cons head of the current stream, right? Because that doesn't satisfy the predicate, so that's going to be there. And what about the tail? So in the tail, we should also keep applying the filter, right? So we create a thunk where we filter on the tail of the stream. Yes, you can build fold on the stream as well, but you have to sort of fold is okay. So just to finish this, right? That's all is filter is. So filter takes a alpha to Boolean, right? That's the predicate. It takes an alpha stream and returns an alpha stream where any element that satisfies this predicate does not is not present in the resultant stream. Sarthak has a question which says, is it possible to build a fold on the stream? Yes, you can build a fold of the stream, just like you build a map on the stream. You have to be cognizant of what the return type is, right? Fold. So think about this question, right? Is it sensible to ask what is the sum of all elements on an infinite stream, right? That is sort of asking the same question as can I build a fold? Sum of all elements on an infinite stream is not a sensible question, right? But you can still make it a little bit sensible saying what is the sum of all elements up to some n, right? First n elements, can you get me a sum? That's the sort of thing that you can build. You cannot asking for sum of all elements in an infinite stream does not make sense. And similarly, fold that you define um, without a notion of without a notion of when to stop is not sensible. I was seeing its use in filtering. Filter is like more like a okay. So the thing that makes filter work and fold not work, right, is the return type. So filter returns you a new stream. So I'm always constructing a different stream. Yeah, you can do all the things, right, as long as what you return is a stream. So you shouldn't if your function depends on producing a single value which is not a stream or a list or something, that's not going to work, because that would by definition mean that um, you're producing some value that is the result of observing all the values in the stream. Filter here is very specific, right? Ravi is um, asking what about fold for is the predicate true for all the elements in the stream, but the return value is a stream, right? That's what makes this work here. So because I'm returning a new stream, I am allowed to stop the execution at some point. But if you say, give me this is the same question as asking filter everything and then give me a list of all elements. That is not going to work, right? So a specific type of fold will work, right? Where the result of the fold is going to be a stream. I hope that makes sense. I mean, I'm very hand wavy here, but that's the idea. So you cannot write a function that sort of expects to produce something that is not a stream, that won't work. Or you have to stop somewhere, right? You either have to say, I'm going to take the first 10 elements where the result is not a stream, or you keep producing infinite data structures, right? Filter and map and so on, all produce a stream as a result. All of those will work. So if your fold sort of folds over the thing and produces a stream, then it will certainly work. So here is an example, right? Um, let's say I have um, this tweet example, right? You can imagine every tweet is associated with a timestamp, and you want to produce a stream which will have each element in the stream is going to count the number of tweets that are produced every second, right? So of course, more than one tweet is going to be tweeted every second. So what the stream does is it accumulates things, right? It still does the accumulation, but for a limited period of time. It accumulates things for a second, and you accumulate it for a second, you produce a new stream. So the result is going to be a stream. It doesn't say I'm going to accumulate it and produce it for the entire. I mean that the question doesn't even make sense. What does it mean to say I'm going to produce uh, the frequency of tweets forever, right? Forever is not has not yet happened. So anything that returns a stream will work, right? You can do fold and all your fancy operations as long as it produces a stream. Does it sort of give you an intuition? Imagine writing something right here, which takes this infinite list of numbers or something, and then sums up the first, sums up every 10 numbers, right? It sort of accumulates the 10 numbers, gets the sum, and then returns you a new stream, which is the sum of all numbers there. That is certainly possible. Try to write that function. That will be a good exercise to know what is possible. Okay, really good questions. Any other question? We'll look at a few more examples and sort of will tell you more about how to program with this. It's a little bit mind-bending, right? So it's sort of you have to sort of think about data differently. So far we've been thinking about data as a static thing, right? That's like there, and then functions map over it. Now it's inverted, right? The functions are there and the data maps over it, keeps flowing through it. There are nice examples in the sequel. So let me continue. So here is filter, right? So filter takes a predicate, right, and filters out all the elements that satisfy the predicate and returns you a new stream. So here is an example where I take 0 ones, right, and I filter all the elements that are equal to 0. So what would it produce? What is the result of this function? So I take 0 1 stream, I filter out every element that is 0, and I take the first 10 elements. What would be the result? Just to make sure we're all following, right? Okay, good. Okay. Is it 5 ones or 10 ones? 10 ones, right? Because this is going to produce a stream, and then on that stream, I'm going to take 10 elements, right? So 10 ones. So that's the idea. So this produces an infinite stream of ones, and on which I'm taking 10 elements. So it's 10 ones. And one thing that I want to sort of say here, right? The flexibility of functional programming, right? So, I mean, this is true with other languages as well, but in OCaml, it's sort of nice and easy to write this predicate, right? So we've used equality before. So I'm just using equality as a function here, which I'm going to partially apply with 0. So what I get is a predicate, right, which when applied to 0 returns true, which applied to any other number returns false, right? So this way of writing succinct code is what I believe that OCaml is useful for, which is that it's very close to how you would write a mathematical specification, right? So this is if you understand what is going on here, I mean, this is a very succinct way of writing code, and this is not just for being clever, right? When you want to maintain large software, I tend to write and maintain large OCaml software. Um, the ability to write code that is very short and still makes sense, right? It's not cryptic. It's not cryptic like C. It's not like one of those mumble jumbles of combining multiple operators where you have to remember the precedence and so on. The rules are very simple, right? There is no precedence table to remember. There is this idea of a function, and you are partially applying it. That is all that is going on here. And I sort of wanted to point that out. Okay, so another function that will come in handy later is this function called zip. So what is zip going to do? It's going to take two streams, S1 and S2, right? And it's going to combine the stream to create a single stream. And the function for combination is f. So f is a function that takes two elements, right? One from S1 and one from S2, and then it is going to return a result, which will be the element that is present in the resultant stream, right? So how does it work? So it returns a new stream. So cons f applied to head of S1 and head of S2, right? That will be the new head. And for the tail, it is simply a recursive call on the tail of the streams, right? So it takes an alpha stream, beta stream. It takes a function that goes from alpha to beta to gamma, C, and then it gives you a gamma stream. Okay, so that's the zip function. Zip is very powerful. We'll come back to zip later. So here is a way of combining two streams into a single stream. So I take 0, 1 stream and 0, 1 string stream, and I return a new stream, create a new stream where I just each element in this new stream is a pair of one element from the 0, 1 stream, one element from the 0, 1 str stream. So if you run it, you get 0, 0, 0, and you get 1, 1, 2, 2, and so on. I don't know whether I have. I mean, I can write it here. So if you take 10 elements from the stream, you get 0, 0, 1, 1, 2, 2, and so on. So it's a nice little function. We will use this function later. Okay, that's zip. Of course, you can do zip on a list as well. We haven't seen zip on a list, but it's a useful function to have. So here is a use of zip, right? Where I take the 0, 1 stream. Right, that's the first one. It's a stream with 0, 1, 0, 1, 0, 1 until infinity, right? And I take the 1, 0 stream. I create the 1, 0 stream by dropping the first element. So I get 1, 0, 1, 0, 1, 0, and so on. I use zip to add the streams together. So each element in the resultant stream will be 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1, and so on. So the resultant stream S is a infinite stream of ones. Okay, so you get an int stream, which is an infinite stream of ones. You can take 10 elements and see that it's an infinite stream of ones. Okay, so those are some simple examples. So there are some clever ways of constructing well-known ideas using streams. In particular, there is this idea of sieve of Arithenesis, which is a neat way to compute primes. I don't know whether you've seen this earlier, but anyway, we'll sort of go through the details. So what you're going to do is to build a stream of prime numbers. Okay, so the way we are going to build it is you start with a stream, right, that has 2, 3, 4, 5, and natural numbers up to infinity. And the idea is that at every step, the head of the stream is a prime. So 2 is a prime number, right? So we take 2, we take the tail of the stream. So that's 3, 4 up to infinity. And what you do is to filter out all the elements that are perfectly divisible by this prime element. So what are the elements that are perfectly divisible by 2? All the even numbers are gone, right? And you'll have a stream which is just the just a stream that starts from 3, right, and goes 5, 7, 9, and so on up to infinity. And you sort of recursively apply primes on this, right? So 3 will be a prime, right? And you apply the same principle. You sort of go through the rest of the stream, the tail of the stream. You remove all the elements that are divisible by 3, and you get a new stream. And in that stream, the head is a prime. You keep doing this. So you will neatly produce all of the prime numbers. So that is what I've described here, right? So if you start from 2, 3, 4 up to infinity, P is a prime number. The head of the stream is a prime number. You create a new stream, S prime, right? Where S prime is just the tail of the tail of this, where every element that is divisible by the prime number is removed. Okay. So here is an example, which is exactly what I mentioned earlier. In the first step, the prime is 2, right? You start from infinite stream of natural numbers from 2. So the prime number is 2. The new stream has all the even numbers removed. So you have 3, 5, 7, 9 up to infinity. So you keep applying the same principle again. In the second step, the prime is 3, and you remove every number that is divisible by 3. So 9 is gone, right? 15 is gone, and so on. And you keep doing it. So that's the whole idea. That's the principle of producing primes. So let's build a stream of primes this way. Okay. So the first thing we are going to do is, so we started with this idea of a stream of prime numbers from 2, right? So we don't have a function for doing that. So we will write a stream that will give us a stream of natural numbers from n. So we call this function from n. So given a number, it just returns you a natural number stream from n. So how is it built? It's a recursive value, right? A recursive function from n. The first number is n, right? And the subsequent number is n plus 1, recursively called on from. So first number will be, say, 2, and the next number will be 3, and you will keep on doing this. So you will essentially end up having a stream that goes from 2 to infinity, right? So here is a way to construct an integer stream that goes from 2, 3, 4 up to infinity. So here is the definition of primes, right? What did we say? So given the current stream, the head of the stream is a prime number, right? You take the head of the stream, that is a prime number. So what are we going to produce? We are going to produce a stream of prime numbers, right? So I'm going to produce a stream of prime numbers. So the head is going to be a prime number that I just picked up. What is the tail going to be? In the tail, you want to filter out all the elements that are divisible by this prime number, right? But also apply the prime number principle on the same stream, right? So get the tail of the current stream, this stream here, filter out all the numbers that are divisible by this prime. So x mod p double equals 0 is going to filter out all the numbers that satisfies this predicate. So you filtered out all these numbers, and then you call primes recursively on it because we want to extract the primes from it, right? Whenever you call, whenever you extract, say, the prime number, the first number will be a prime number. The next number should also be a prime number. So we call primes recursively on it. Okay, so that is just so whatever I described here is what I've sort of written down here. It's a bit mind-bendy because we are tying knots a little bit here, right? So we take primes and recursively call it, and recursive data structures are always a little bit mind-bendy. So that's the definition of primes, and we know that primes start from 2. So for the initial stream, we pass the stream that is generated from 2, infinite stream of natural numbers that starts at 2, and that will return you the prime stream. So prime stream is the stream of prime numbers. That's it. So you can take the first 100 prime numbers, for example. So you get the first 100 prime numbers. Essentially, this is doing the work on demand, right? Whenever you ask for 1000 prime, it will give you the 1000 prime. Yeah, so that's a nice way to construct prime numbers. Any questions here on any of this? Can you try primes from 1? 1 is 1 will fail, right? Because you'll remove every element that is going to be divisible by 1. So this won't ever terminate. You enter into an infinite loop because this filter will fail. It's a good reason 1 is not a prime number. Okay, there is another question. I will answer that. So the reason why it fails here is I said from 1, but this filter, right? So any number is perfectly divisible by 1. So this filter, if you look at filter definition, if the head is predicate is true, it recursively calls filter. So we are checking whether 2 is divisible by 1. It is. So we are going to recursively call filter. 3 is divisible by 1. Recursively call filter. It's spinning an infinite loop here. It's a tail recursive call, so it doesn't stack overflow. So 1 is not a prime number. Okay. So let me put it back to 2. This will work. So the other question was, what is the at operator? Yeah, I should have sort of explained what it is. It's just a helper thing to say this bracket goes all the way to the end, right? So why is it useful? Let's say I have I don't know, X, Y, Z, right? So if I want to say I want to write this, right? And then Z applied to say A. It's more like a thing for brackets. So instead of writing all the brackets here, right, where I want to say go evaluate this one first, and then apply X on the result, right? I can write it like this. I'll keep it here. X at Y at Z A. It's just it's not a function. It's more of a parser helper, right? So that's all there is. It's sometimes nicer because I can avoid 3 brackets here, right? So instead of writing a bracket here, I can just say primes here. Yeah. Does that make sense? Yeah, there are a few things like this which I should probably avoid. But anyway, so you don't need this here. Just do. Okay, good. So we produced a stream of prime numbers. Let's look at one more example. So here is a neat way to generate Fibonacci sequence, right? So we know what the Fibonacci sequence is. We've been sort of doing Fibonacci almost every lecture, but here's a different way to consider Fibonacci. Let's consider the Fibonacci sequence, right? So 1, 1, 2, 3, 5, 8, 13, up to infinity. Let's sort of consider the tail of the Fibonacci sequence, right? The tail of the Fibonacci sequence is 1, 2, 3, 5, 8, 13, and so on. So it's 1, 2, 3, 5, 8, 13, and so on. Let's add the 2 streams, right? Let's sum up the 2 streams. What do you get? So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on, right? What is the relationship between S3 and S1? S3 is the tail of the original Fibonacci sequence. So this is the Fibonacci sequence, right? And S3 is simply the tail of Fibonacci sequence S1, right? So the sort of surprising bit is this, right? So if you are able to get S3, which is the tail of Fibonacci sequence, and you prepend just these two elements, 1 and 1 to the front, right? You get S3 and prepend 1 1 to the front, you get the Fibonacci sequence, right? And this all seems true but very weird. Why would you even work it this way? But this gives you a nice way of constructing Fibonacci sequence. So here is the entire function. So what do we do here? We are going to prepend 1 and 1 to the front, right? So cons 1. So I'm defining a Fibonacci sequence, right? Letric fibs. I'm defining a Fibonacci sequence where I prepend 1 and I prepend another 1. And what did I do here? I took the Fibonacci sequence, I took the tail of the Fibonacci sequence, and then I added them together, right? And the way we add two sequences is zip, right? So the rest of the sequence is just going to be take the original Fibonacci sequence here, take the tail of the Fibonacci sequence, and then add them together, right? So that is going to give you sort of a recursive definition, right? That is why um, looking at it by just reading the code might not make sense, but it's really what is happening is this, right? We're actually defining this by defining this, which is in turn defined by defining this. Yeah, okay. So all we did is we prepended 1 and 1. The sequence that we are defining, we take that we take the tail of a sequence and we add them together, right? And when you zip them together, what you get is this S3, and that is what we need. So that's the integer stream of Fibonacci sequence. To confirm that it works, right? Here is the first 30 Fibonacci numbers. It takes a while, actually. I'll come to that point. So it takes a while. So it produces all the Fibonacci numbers from the first 30 Fibonacci numbers. Uh, yeah, it took a while, right? So you should sort of look at why it takes a while. It takes a while because each time we force the computation, right, we actually compute the Fibonacci sequence twice. It is not obvious here, but every fibs definition here is a fibs definition that includes a zip internally, right? It is hard to write down the stream version of it pictorially, but what is happening here is equivalent to this definition that we have of this inefficient way to compute Fibonacci, right? This exponential way of computing Fibonacci, which is fib of n is fib of n minus 1 plus fib of n minus 2. So every time you increase n, the cost of computing the nth Fibonacci number is increasing exponentially, right? So that's what is happening here, and that is why this implementation takes a lot of time, right? And if you ask larger numbers, it's just going to crawl to a halt. Yeah, so we will look at how to fix this in the next class, and then we will also look at a few other things which talks about how to make these streams efficient. But that's the observation. So of course, I've showed you like what I would call elegant ways of computing Fibonacci and computing primes, right? But these are not the most efficient way to write either primes or Fibonacci number, right? But how can you retain the elegance but still make it efficient is what we are going to see in the next class. I'll stop here. If you have any questions, I'll hang around for a minute or two, and then we'll disperse. This is quite clever, this definition of Fibonacci. I didn't come up with it, obviously. Okay, so what I would suggest is go through these two examples, right? Sort of, there are a lot of things that you can express as nice prime numbers. They're not really obvious, but these two are sort of prototypical examples of what you can do with stream programming, right? This is just fun in functional programming. This is not like, I wouldn't call this practically minded functional programming, but these sort of tell you something about the nature of these problems, right? So I think these are nice to study anyway. Go have a look at Fibonacci sequence and primes today, and then try to convince yourself that they do work. Right? Um, anyway, so no questions, it seems like. So I will stop here, and then we can meet tomorrow. We'll look at how to make these faster. Thank you.